A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Today we'll be talking about the X-ray diffraction technique. This is one of the tools that is used for investigating the crystalline nature of the materials. Basically, in today's lecture we will discuss the importance of X-ray diffractions that is used for the material characterization. Before going toward the X-ray diffraction, we need to know diffraction, that what is diffraction actually, and then moving toward the X-ray diffraction, why X-rays is often used to diffract at the crystalline material, why we are not able to use some other electromagnetic radiation instead of X-rays like visible light, ultraviolet light, or gamma rays, or some other sort of electromagnetic radiations. And we need to know the crystal structure and the relationship between the crystal structure and X-ray diffraction. There are different methods followed to perform the X-rays diffraction, and we often have some objective to perform the X-ray diffraction, just like the phase analysis, texture analysis, stress analysis, or the particle size analysis. So we will also be going through that. Material characterization. In material characterization, it is often important to evaluate the structure and of the material, because structure and property are closely correlated to each other. For structure characterization, we do the X-ray diffraction or the diffraction technique, and for that we have X-rays and electron diffraction. In electron diffraction, we do some we do microscopies as well, and also do some spectroscopy as well. Similarly, we evaluate some of the properties of the material for utilizing or using that material for a particular sort of applications, just like mechanical property we need to evaluate, or electrical property we need to evaluate. So looking toward the history of X-ray diffraction, in 1665 diffraction effect observed by an Italian mathematician, Francesco Marie. So that was the first diffraction effect that was observed. And in 1868, X-rays discovered by German scientist Röntgen. That is why it was also called as Röntgen rays. Further development were made in 1912, where the discovery of X-ray diffraction by crystal, that is actually called as a Van Laue method, where it was discovered that we can diffract X-ray by using a crystal. And finally, in the same year, in 1912, there was also Bragg's discovery, that is often used as standard method or a standard technique to perform the X-ray diffraction, or to calculate the parameter from the X-ray diffraction, just like the lattice spacing or the lattice constant or the diffraction angle and all other parameters. So look, coming towards the electromagnetic spectrum, we have electromagnetic radiation of different wavelengths, starting at very high, from very high energetic radiation, just like gamma rays, X-rays, and coming towards the low energetic radiation, just like radio waves or audio waves. We have some sort of light in between that is a visible light, and that has a wavelength around 10 to 3 nanometer, and its different colors are present in the visible regime. So especially the 7 colors. So we often use the X-rays for that. And for X-rays, the wavelength of the X-rays is around about 10 to the power minus 1 nanometer. That is equal to 1 angstrom. So how we can generate. So a question arises why we are looking toward the particular sort of the so a question arises why we are using X-ray for the diffraction of crystalline material, because often for the diffraction to occurs, the size of the grating should be comparable to the size of the wavelength of the upcoming radiations. Here, if we look towards it, the atomic spacing is around about 1 angstrom. But if we are looking toward the wavelength of the electromagnetic radiation, so X-rays come in the region where its wavelength is around about 1 angstrom. So better diffraction can occur at using the X-rays for this for crystalline for materials. So how we can generate X-ray? This is most important. The generation of X-ray is also a bit important because it can be done by the incident electron beam that move electron between the there is a transition of electron between the energy levels, or the ejection of electron between the different level, leading to the generation of X-rays. So we have different machine for that, where we use some external potential difference, and that is utilized to generate X-rays. We have different crystal structure and previous lattices that are basically a standard lattices or a standard structure. Among that we have 7 different crystal systems, and from this 7 different system we have 14 different previous lattices. So that is actually the basics of crystallography. So diffractions, a diffracted beam may be defined as a beam composed of a large number of scattered rays mutually reinforcing each other. So here we can see the diffracting beams. If there is a radiation falling on a particle, so what happen? We have two possibilities: whether the particle will be scattered and that will be randomly move in different direction, or whether the particle will be diffracted that interact with the crystal and are mutually reinforcing each other and are collected at the detector. So the scattering mode is a random arrangement of atoms in space, giving rise to scattering in all directions, that is weak effect and intensities. So by atoms arranged periodically in space, that is actually the crystalline nature of the material, in a few specific directions satisfying the Bragg's law. So there is strong intensity of the scatter beam, and from the diffraction we see that no scattering along the direction satisfying the Bragg's law. So we have this is a simple diffraction, and we see the size of the diffraction grating is equal to D, and the diffraction occur at the point where we get high intensity peak at that particular point. So this is another example of the diffraction, and we can see at the photographic film we have a bright dot that is showing high intensity peak at that particular point. We have Young double slit experiment, that is basically a famous experiment for this particular methods, and where diffraction occurs, and we have constructive interference at the end and destructive interference as well. That depends upon the path difference between the waves. So the interference might be constructive interference or it might be destructive interference, and it depends upon the phase difference of that particular waves that are created. Here we can see the phase difference of 0 degree between the waves, the phase difference of 90 degree, and the phase difference of 180 degree. So this is a Bragg's method that is showing the diffracted beam that is diffracted from the interior, from the upper plane and from the inner plane, and the scatter or the diffracted beams are recombined and that are collected, or maybe that are scattered at different directions, where we have a simple technique for that. And in this case, D is which is actually the plane spacing, is equal to D is equal to A divided by H square plus K square plus L square under the root, and the path difference must be integral multiple of the wavelengths. So this further detail of the Bragg's law, where we have D is equal to n lambda divided by sine theta, or in very simple case we have 2d sine theta is equal to n lambda, and we have in the first figure we have two beams that are diffracted from the outer and inner planes, and in the second figures we have three beams that are diffracted from the outer and inner surfaces. So we have geometry of the Bragg's law, in that the incident beam the normal to the reflection plane and the diffracted beam are always coplanar to each other. So the angle between the diffracted beam and the transmitted beam is always 2 theta, that is usually measured in 2 theta. And since sine theta and this n lambda is less than 2d, and for n is equal to 1 lambda is less than 2d. So lambda should be less than twice the d spacing we want to study. So order of reflection is like that we can write the Bragg's law like lambda is equal to 2 sine theta divided by 2 sine theta into d divided by n. So a reflection of any order as a first order reflection from planes that is real or fictitious, spaced at a distance 1 over n of the previous spacing. So for that, with lambda is equal to 2d sine theta. So we have nth order reflection from HKL planes of spacing d that may be considered as a first order reflection from the NH, NK and NL planes of spacing. So this is particular discussion on that. So we often use the reciprocal space for that, and that is used to describe the Fourier analysis of electron concentration of the diffracted pattern. So every crystal has associated with its crystal lattice and a reciprocal lattice. So diffraction pattern of a crystal is the map of reciprocal lattice of the crystals. So this is actually the diffraction beam from sodium chloride NaCl that is used, and here the peaks are identified. Each peak is identified and the planes from which this peak has been scattered is mentioned. Just like you see the higher intense peak among all these peaks is a peak that is diffracted from the plane 200 in this particular case. We have different methods for the diffraction to follow, just like we have powder diffractometer, where we need a powder sample for the diffraction, and this is a simple method where we have a source for X-ray and the specimen is rotated at different angles and the diffracted beam is collected at the counter. So the calculated pattern for a cubic crystal is like that. We have the intensity that is compared and the different peaks are characterized. We have different methods for the diffraction techniques. These are actually the diffraction methods that depends upon that have different specifications. Just like we have live method, in which where we use variable wavelength for that, and the angle is fixed, the sample is fixed, and the specimen should be single crystal. We have a rotating crystal method, and in that we use X-rays of a fixed monochromatic radiations. So in that case the angle is variable, we are rotating the sample at different directions, and again the sample specimen what we need to be investigated is a single crystal. And finally, the method that is widely used and we often use for characterizing our sample is the powder diffraction method, in that the wavelength is fixed, the wavelength of X-rays is fixed, but the angle is variable, and the sample is rotated through the 100 degree or from 0 to 100 degree at different steps, and the diffracted beams are collected at the collectors. So the specimen for this should be powders. So live method is a simple method where we have incident beam that is passing through a crystal, and we can collect the diffracted transmitted beam from the at the films. So we have transmission in that case that is possible, which create the zone axis, and reflection is also possible, in which the zone axis changes at different angles. So in the case of reflection, the crystal location or the sample location is being changed. So we use single crystal, white radiation, and determining crystal orientation and quality. So this is a rotating crystal method, in which we determine of unknown structures. We want to measure, we want to investigate unknown structure. We have X-ray source in that, and the X-ray source is directed in a specific direction, and that fall on the sample. And from the sample we have cylindrical film. Around the sample we have cylindrical film, where the reflected beam is collected at the film, and we can get information out of that. So we have powder method, that is a simple method and most commonly used method. Incident beam is fall on a sample that is present in between the in between the films. So the diffracted beam is collected at the film, and we can get the diffracted beam, and from the when we investigate the diffracted beam, we can get the information out of that. So we can index that particular pattern using standard techniques, and for that we have used the angle 2 theta instead of theta. So just like when we are using the Bragg's law, that is equal to n lambda is equal to t sine theta, and the spacing between the cubic spacing should be equal to d is equal to a divided by h square plus k square plus l square, where h, k, l are the indices of the planes, and from that we can get the values lattice parameter. So we can get the diffraction from a variety of material. Just like in this slide, we have crystals that gives us regular pattern and regular peaks, which are diffracted from particular planes. For performing the X-rays of liquid or amorphous solid, we use very different peaks or broad peaks, and that are not well characterized. And if you use monoatomic gas, the peaks is a bit different, and that is actually the scattering processes. The intensity of diffracted beam, we can get the polarization factor, the structure factor, the multiplicity factor, the Lorentz factor, the absorption factor, and the temperature factor out of them. So once we get the peaks or the pattern of a particular X-ray from particular X-ray diffraction technique, we can compare this peak with the standard peaks that are actually JCPDS cards and IC, and from that we can get the information. So this is something what we got very interesting result from this lecture, that X-ray diffraction is a very useful to characterize material and get different information, just like especially the phase analysis, the lattice parameters. We can determine the lattice parameter of the samples, and the strand determinations are also found, and the texture and orientation analysis for particular samples, and order disorder transformation. Choice of correct type of method is critical for the kind of work one needs to do. So we have powerful tools for that. So this is something we have about X-ray diffraction, and this is very interesting because we can get very interesting information using a very simple method, which is actually the X-ray diffraction method. And from this method we can get especially the lattice parameter and the phase, because some of the material exists in different phases. So we can also find the correct phase from the pattern that is issued from the X-ray diffraction technique, and then we can compare that with the standard JCPDS cards. So this is something of today's lecture. Thank you very much.